Good evening, everybody. Science of Santa. This is just a short talk, a little bit of a tongue-in-cheek stocking filler for the festive season. So I'm asking the question, is Santa compatible with the laws of physics? As I'm a physicist, a scientist, when I was asked by my nieces and nephews, does Santa exist? Well, I didn't want to lie to them, so I thought, let's check it out. Just how many laws of physics does Santa break? So I'm fairly sure we all know that Santa is, at least allegedly, a portly, jolly fellow with a white beard and a penchant for wearing red suits. So although this does display questionable fashion sense, that doesn't mean he can't exist. So the question is, what about the claims made for this gentleman? He allegedly visits all households on Christmas Eve to deliver presents to all qualifying children. And how do they qualify? Well, they make sure they're on the nice list. Can we reconcile this statement about him visiting all children on Christmas Eve? Can we reconcile that with our understanding of physics? And in particular, what about any of the talks that I've given? I've given you, I don't know, about a dozen or more talks, and I've got quite a few dozen. What I've done is pick out little bits of those talks and use the science in those talks to answer this question. So let's take that statement again in its entirety. Santa visits households on Christmas Eve to deliver presents to children. We're going to pick that apart scientifically, forensically, one bit at a time, and ask, is that reasonable? Let's start with, how many children does Santa actually visit? Well, the Earth's population is about 8 billion these days. I believe about a quarter of the population are children, and let's imagine that 50% of them are eligible for Christmas presents. In other words, Santa delivers Christmas presents even perhaps to children in households which aren't necessarily identified as Christian. So that means about 1 billion children get Christmas presents. That's assuming that the naughty list has no children on it and the nice list has 100%. Now, any parents or grandparents out there will probably take issue with that particular split, but let's just assume it's 0 and 100, just to give us a nice round number of 1 billion children. Okay, Santa visits these 1 billion children. How does he get around? What's his mode of transport? Okay, it's a sleigh pulled by flying reindeer. So we can ask, can reindeer fly? Well, we know that insects fly, and we know that birds fly, and we know that pterosaurs fly, though you don't see them very often these days. And even some mammals fly. So what about reindeer? Well, if they can fly, they choose not to do so for a lot of the time. There is very little evidence for flying reindeer. But remember, scientifically, we must recognize that absence of evidence is not evidence of absence. Just because we have no evidence, we have no photographs of reindeer flying, just because we have no photos of them actually flying doesn't mean they can't. It just means when they do decide to fly, no one's around to see them. So the jury is still out on that particular point. How fast would Santa and his sleigh have to fly in order to visit all of the 1 billion children in a night? Well, he would have to travel at least 2,000 kilometers per second. That's assuming he visits all these children. Let's assume they're distributed over the world, over the globe, and he's got about 36 hours to do this. Remember, it's not just 12 hours of night time, because if he uses the time zones of the world in the sensible direction, he can actually stretch it out to a full 36 hours. So 2,000 kilometers per second sounds really fast, but actually it's only 0.007 times the speed of light, shown here as the lowercase c for brevity. So if he's moving at less than 1% of the speed of light, he's in no danger of breaking any of the laws of physics. And in a separate set of talks that I call Fiat Lux meaning let there be light, I talk about the nature of light and the fact that light does indeed have a speed limit. No object can travel through space faster than light can travel in a vacuum. But as I say, Santa's only at a fraction of 1% of that speed, so it's not a problem. When we look out into the universe, we see that the universe is expanding, and space can actually expand such that galaxies are moving away from us faster than this speed limit of the speed of light, but that's an entirely different issue. We're talking about objects moving through space, in this case, objects moving through the Earth's atmosphere. If he does really move that fast, wouldn't the sleigh get really hot, and wouldn't the reindeer get really hot, and we'd end up with roast reindeer? If we think about meteors and asteroids entering the Earth's atmosphere, the air in front of an asteroid, for instance, coming into the Earth, the air in front of the asteroid gets compressed and heats up, and hence the body glows. And a meteor is just a small example of that, a tiny grain of sand. But still, the atmosphere gets compressed, the meteor gets hot, and it glows, which is why we see a meteor as a shooting star. So, if moving really fast through the atmosphere heats things up, how can we get around this? We know from other talks, such as the ABC of stellar evolution. In that, I describe how stars get hot in the first place. A star is born when a large cloud of gas gets compressed, and the compression of that gas cloud heats up the star to the point where it can then undergo nuclear fusion and then self-sustain the heat. But everybody knows that compression produces heat because, for instance, when you pump up a bicycle tyre, you know the tyre and the pump get hot. So although it is part of stellar evolution, it's also part of our everyday experience. When you compress air, things get hot. Even if the sleigh was really aerodynamic, that would still be the case. It would still be moving so fast that you would expect it to get hot. So shouldn't the sleigh be white hot? If compression produces heat and hot objects radiate light, then Santa and the sleigh ought to be very easily visible. And you could argue, well, maybe they were. If you go back 2,000 years, there was a very bright light in the sky, the Star of Bethlehem. It's a bit of a push to say that was actually Santa's sleigh, because haven't we got the timing all wrong to assume that Santa is actually responsible for the Star of Bethlehem in the first place? But in terms of seeing bright lights in the sky, you could say, well, yeah, people do claim to see bright lights in the sky. Another talk on UFOs describes how bright lights in the sky can be interpreted as either spacecraft or extraterrestrials, or maybe we're seeing Santa. But there is a type of material that we know about, a type of matter that we know about, that does not glow when it gets hot. Virtually everything we understand, all the normal matter around us, if you heat it up enough, it will glow. But there is matter out there in the universe. We can't see it because it doesn't emit light, but it doesn't absorb light either. It doesn't reflect light. It doesn't interact in any way with any electromagnetic waves, whether they be visible light or ultraviolet or infrared. So it's a rather unusual type of matter called dark matter. But is there any reason, if dark matter does exist, and we believe it does, is there any reason why Santa and his sleigh aren't made of dark matter? In which case, even if they get really hot by moving through the Earth's atmosphere, they wouldn't glow. And therefore, that might explain why we don't see Santa's sleigh zooming across the sky on Christmas Eve. It also explains, because dark matter doesn't absorb or reflect any light, if Santa and his sleigh was made of dark matter, well, that explains why it doesn't show up on radar, because radar is just radio waves. If you shine radio waves, fire radio waves at the sleigh, they would just go straight through and they wouldn't be reflected, you wouldn't get an echo or a ping, and therefore it wouldn't show up on radar. Okay, let's go back to the original statement. We're talking about 1 billion children. Santa visits them and he enters the households to deliver the presents. So, how does Santa get down so many chimneys? He would have to squeeze down a huge number of chimneys each second if he wanted to visit a billion children in one night. And we've just said in the early part of this talk that Santa is allegedly a rather portly fellow. If he's really rather rotund, how can he possibly get down a chimney? Well, here quantum theory comes to our rescue, because quantum theory describes atoms and molecules, and generally speaking, small things. And we know, for instance, that an atom is made up of a nucleus surrounded by electrons. Now, if we replaced the electrons with a different particle, an electron has a sort of heavier cousin, if you like, called a muon. If we replaced the electrons with muons, then all the atoms would be a lot smaller, by a factor of about 200. So if somehow Santa managed to figure out how to do this and replace the electrons in his atoms with muons, then all of his atoms would be 200 times smaller. And so instead of Santa being somewhere between 1.5 and 2 meters tall, he would only be about a centimetre high. And therefore he would fit down a chimney no problem whatsoever. He would actually be a little bit heavier as well, so again he would go down the chimney very easily. But you might say, well, that's all very well, but there's a lot of houses or apartments, etc., that don't necessarily have chimneys, especially modern domiciles. So how can Santa get inside a house or a home or an apartment that doesn't have a chimney? Well, again, quantum mechanics comes to our rescue, because it is possible for one solid object to pass through another. Indeed, it's possible for fundamental particles, whether they be atoms or molecules, to pass through solid matter simply because atoms and molecules are, yes, they're made of lots and lots of subatomic particles, but there's in principle a lot of gaps between them. And there's a quantum mechanical principle that says one object can pass through another. It's not necessarily very likely to occur. We can see it happening on the atomic scale. In fact, we build microscopes that are built on the principle that this can happen. It's called a tunneling microscope, and this property is called tunneling. So in principle, Santa could go from outside a house to inside a house by tunneling through the solid walls. He doesn't need an open door or an open window. We know this is possible from quantum theory. It usually happens on the small scale, and we don't usually see it happening on the large scale, but maybe Santa has figured out a way of using this to his advantage. Let's go back to that statement. So we're visiting 1 billion children in households, and we're doing this on Christmas Eve. So how can Santa make so many deliveries in one night? Even travelling at relativistic speeds, or at least a fair fraction of the speed of light, how could everything be done in simply one night? Let's assume that's about 36 hours or so. Well, again, quantum theory comes to our rescue, because quantum theory tells us that when we're looking at the world of the very, very small and thinking, how do atoms behave and how do molecules behave, there's a lot of things that go on at that level that don't agree with common sense. For instance, if we think of electrons going around an atom, let's just imagine that they are moving in a sense of planets going around the sun. That isn't a very good analogy, but if we just use that for a moment, we can think of electrons going round clockwise and going round anti-clockwise at the same time. We don't see that usually in the macroscopic world. If we have a spinning top, or if we think about the Earth rotating, it's either rotating one way or it's rotating the other way, but it doesn't rotate in both directions at the same time. But our understanding of the quantum world is that this does actually happen. It goes completely against common sense, but yeah, the quantum world doesn't agree with common sense. So if subatomic particles can spin clockwise and anti-clockwise, it turns out they can also be in two places at one time, even though in the world we're used to, an object is either over here or it's over there, but it's not both at the same time. But in a quantum world, that can happen. So maybe, again, Santa has figured out how to use this to his advantage. If Santa can be in 2 places at once, well, why can't he be in 10 places at once? Or 1,000 places at once? Or 1,000,000 places at once? None of that actually breaks the laws of physics as we understand them when we think about quantum theory. So maybe that's okay for Santa. If you don't like that and say, well, no, I really want Santa to be in one place at a time, how can he possibly visit all of these places in 36 hours? Well, there is an alternative. Maybe he can actually manipulate space and time. Now that sounds rather exotic and very sci-fi, but we know that space and time are affected by the presence of mass. Normally, we don't see the effects very strongly. We can measure them with very precise instruments, but if we look at very massive objects, for instance, like stars, or very dense objects like black holes, we realize that they do indeed change the way space and time work. Again, it's rather removed from our everyday experience, but that is the way the universe works. So if it's possible for matter to distort and expand or compress space, then maybe Santa has figured out a way of manipulating space such that instead of having to visit all of these various places, he shrinks the space between him and the delivery point such that, in a sense, all of these homes come to him rather than he having to travel to all of these places. Again, that doesn't break the laws of physics as we understand them. So we've got Santa visiting households on Christmas Eve, and he delivers presents. Okay, how can he carry all of these presents? One present, let's assume just one present for each of 1 billion children. How could the sleigh hold that many presents? The sleigh is presumably only a few meters in size, so how could it possibly hold 1 billion presents for the children? Well, even if the sleigh is only a few meters in size, as measured on the outside, the volume of the sleigh on the inside could be larger. It is possible for an object to be bigger on the inside than it is on the outside. And if you think I'm talking about science fiction, like, for instance, Doctor Who's TARDIS, well, yes, but we think it is also applicable if you can distort space and time. As I mentioned before, the presence of matter can distort space. And we believe that, for instance, black holes are an example of an object which are bigger on the inside than they are on the outside. So if these things do exist naturally, then perhaps Santa has figured out a way of making his sleigh such that it's bigger on the inside than the outside. So maybe it is possible to hold 1 billion presents, even though the outside dimensions of the sleigh would make you think that that can't work. Again, there is an alternative way that Santa can do this without breaking any laws, and that is that we believe that space comprises 3 dimensions: forwards, backwards, left, right, up, down. So we can perceive 3 dimensions of space. But some scientists believe that actually space is made up of more than 3 dimensions. It's just that we find it very difficult to visualize and perceive those extra dimensions. And there might be more than 3. Some people believe there's 10 or 11 or 12 dimensions. So maybe Santa somehow has got access to these extra dimensions, and he simply stores the presents in those dimensions where we can't see them. He somehow moves the presents into that dimension, and then when he visits all of the various households, he simply pulls the presents out one by one from this other dimension and then places them under the tree. Again, I'm not sure how he does that, but it doesn't break any laws of physics. We simply do not know how many dimensions of space there are, even though we assume there might only be 3. But you might say, quite reasonably, it's all very well saying that these feats might be possible, but wouldn't any of these things need a huge amount of energy? If we're talking about Santa and his sleigh and 1 billion presents moving at very high speeds, wouldn't that need a ridiculous amount of energy? Well, yes, it would. But maybe Santa has got access to a huge amount of energy. For instance, his sleigh might be powered by a black hole. A black hole, in principle, could power a starship and send us to the stars, not simply to visit other planets within our solar system, but literally explore other stars in the Milky Way. A black hole that was strong enough to power a starship, or indeed a sleigh, wouldn't have to be huge. A black hole about the size of a grain of sand would be enormously powerful. Again, I don't know where you get these black holes from, but in principle, if you had one, you would have a huge amount of energy available to you. But there's an alternative that we've been overlooking. There's an energy source, an absolutely huge energy source that we haven't mentioned. It's the elephant in the room. What happens to all the mince pies? If Santa could convert the mass of all the mince pies that are left out for him into energy, he would have a huge amount of energy. Remember, the exchange rate between matter and energy is given by our friend Albert Einstein, E equals mc squared. If you know the mass, you can multiply by the speed of light squared, and that tells you how much energy is, in a sense, locked up in that mass. So we can do that for a mince pie. So if you don't like numbers, then look away now for the next slide or two. So let's take one mince pie. E equals mc squared, and the mass of a mince pie is about 50 grams. 50 grams multiplied by the speed of light squared in standard metric units gives us an energy of 5 times 10 to the power 15 joules. I'll come back to the unit of joules momentarily. If you prefer, you can think of it as almost the same as the unit of energy of 1 calorie. Let's assume that a few % of households leave a mince pie out for Santa. Let's try and keep the numbers simple. So let's take 20 million mince pies, so only a small fraction of the total number of households visited. 20 million mince pies gives us 20 million times 5 times 10 to the 15. That's a total of 10 to the 23 joules of energy. And I appreciate that if you're not a physicist, you can't really imagine what 10 to the power 23 joules is. So let me put it in a slightly different way. Think of a nuclear power station generating gigawatts of power. Gigawatt means it's generating a gigajoule per second, 1 billion joules per second. So a nuclear power station running every second of the day for every day of the year for 1 million years will generate that amount of energy. 10 to the 23 joules is the amount of energy generated by a nuclear power station running continuously for 1 million years. And that energy, in principle, is available to Santa if he can convert all of the mass of mince pies into energy. Okay, how might he do that? How do you extract, knowing the energy is there is one thing, how do you extract E from a mince pie? Well, one option, arguably the most efficient way of doing it, is to take a mince pie and take an antimatter mince pie and collide them together in the Large Mince Pie Collider at CERN. But I'm sure you can see the problem here. We might have 20 million mince pies, but we haven't got any antimatter mince pies. So we have a problem as to where we would get those from. So that sort of doesn't work. Shame, because that would be a very efficient way of extracting the energy. But there is a way to extract not all, but at least most of, or a reasonable fraction of E equals mc squared from a mince pie. There's a process which is not 100% efficient, but it might be 10% or 20% or 30% efficient in terms of the amount of energy you can get out from a given mass. How do you do that? You drop the matter into a black hole. If you drop matter into a black hole, a reasonable fraction of the matter will be converted to energy. Some of the matter will end up going into the black hole, and some of the energy from that matter will be radiated out before the matter falls into the black hole. We know this because we see it happening. We can look out into the universe and we see galaxies which have a large black hole at the center. If that black hole is eating matter around it and a lot of energy is being produced, then that galaxy will be called a quasar. Quasars, the black holes in the middle of quasars, are eating lots of matter, probably not mince pies, I'll agree with that. The matter that's falling in is probably gas, and probably stars are being eaten by the black hole, and as stars fall into the black hole, enormous amounts of radiation are emitted. And we can see these quasars even at incredible distances. These quasars might be on the other side of the observable universe, but the amount of energy that's produced by this process is so vast we can see them even at that incredible distance. In some cases, we don't even need a telescope to see the light that's radiated from these very distant objects. So we know it's a very efficient process. How much energy can be released by dropping a mince pie into a black hole? Surprisingly enough, I cannot find the definitive answer to that. No one seems to have researched this. I can't find anybody who is studying how much energy is released by dropping a mince pie into a black hole. But I'm sure, based on our knowledge and our observation of galaxies, it will be a very efficient process. So Santa will have access to huge amounts of energy if he wants it. So you might say, okay, Santa appears to be able to do wonderful things, and okay, if he can figure out how to do it, he might be able to have enough energy to carry all these things out. But if these are possibilities, yeah, but how does Santa actually, for instance, manipulate quantum theory or manipulate space and time? How does he get a tame black hole on his side? Well, bear in mind, there is nothing to say that Santa has to be human. Why can't Santa be, well, okay, no children ever see Santa because by definition they're always asleep before Santa arrives. So maybe Santa is not human and is a somewhat different creature, although we visualize him as a person, a male with a white beard. Maybe he's got green skin and has other powers that perhaps we don't fully understand. So coming back to the question, is Santa compatible with the laws of physics? Or if you prefer the slightly snappier question, how many laws of physics does Santa break? I think the answer is none. So feel free to draw your own conclusions about the existence, or otherwise, of the portly, jolly fellow with a white beard and a penchant for wearing red suits. Regardless of your conclusion, may I wish you all a very Merry Christmas. Thank you for listening.